Alright, in this part we are going to be looking at a second descriptor of concentration, and that's going to be molarity. Molarity is defined as the number of moles of solute, and a volume of solution that measured in liter. The unit is uppercase M. Okay, so you can think of it as moles per volume, right? That M means moles of solute in liter of solution. So let's say if I want to make a solution with a specified molarity, what you would do, let's say I want to make 1 molar sodium chloride solution. I would measure 58.44 grams of sodium chloride. Okay, that corresponds to 1 mole. I'll put it in a flask. Then I would top the flask with liquid water all the way to 1 liter, mix it well, and now I have 1 molar solution. Okay, so let's see how we can calculate molarity. Calculate the molarity of a solution made by putting 15.5 grams sodium chloride into a beaker and adding water to make 1.5 liter solution. So I have 15.5 grams of solute and 1.5 liter of my solution. So I am given the mass of sodium chloride as well as the volume of the solution. I'm asked to find the molarity. I need to find the moles first because this is given to me in mass. In order to find the moles, I'm going to use the molar mass as a conversion factor. So it'll be 15.5 grams sodium chloride times 1 mole sodium chloride over 58.44 grams will give me 0.2652 moles of sodium chloride. Molarity is defined as moles of solute per liter of solution. So I'm going to take that amount, the moles of sodium chloride, divided by the volume, 1.5 liter of solution. I get 0.177 molar. That's molarity. Alright, now try this one. Pause the video, work it out, and come back and check your answer. Alright, so we're given the mass of ammonia and the volume of the solution in milliliter. So step 1, I'm going to convert the mass of ammonia to moles of ammonia by using the molar mass of ammonia. Then I would convert the volume of my solution from milliliter to liter. Then I'll divide the moles by the volume in liter. I will get molarity. Alright, so let's convert the mass of ammonia. 3.4 grams of ammonia divided by 17.03 grams, I get 0.2 moles. Then I'm going to convert the volume to liter. Then simply I will divide the mole by the volume. I get 1 molar. The same way we used a percent in calculations, we can use molarity in calculations. Okay? Since it's mole per liter, that's a ratio. We can write it whichever way we want. Determine how many grams of sucrose are contained in 1.72 liter or 0.758 molar sucrose solution. We're given the volume and the concentration, and we're asked to find the mass. That means I'm going to go from volume to moles using the molarity. Then I'm going to go from moles to grams using the molar mass of the substance. So I go 1.72 liter solution times the molarity will allow me to convert to moles. Then I'm going to multiply by the molar mass of glucose, sucrose in this case. I end up with 446 grams of sucrose. All right, try this one. Go ahead and pause the video, try it, then come back and check your answer. I have the volume, and I'm looking to find, I have the volume as well as the molarity of the solution, and I'm looking to find the mass. So I'm going to start with the volume, use molarity to find the moles of calcium chloride. Then I'm going to use the molar mass of calcium chloride to find the mass of calcium chloride. Volume, molarity, then the molar mass. I end up with the mass of calcium chloride. All right, try another one. How many grams of copper 2 sulfate pentahydrate we're giving you the molar mass, are in 250 milliliter of 1 molar solution. So I have the volume, I have the molarity, and the molar mass. I'm looking to find the mass. So I start with the volume, convert it to liters. Then I'm going to use the molarity. It's 1 molar, right? This will allow me to convert to moles of the solute. Then I'm going to use the molar mass of the solute to convert to mass, 62.4 grams of copper 2 sulfate pentahydrate. Now keep in mind that those concentrations are for compounds, but if I have an ionic compound, such as calcium chloride, right? So if I have 1 molar glucose, then this is what I have, 1 mole of glucose in 1 liter of solution. But if I have 1 molar calcium chloride, a soluble ionic compound in solution, the ions themselves are going to separate. If you recall, we discussed this in chapter 7. They will separate. That means I'm going to have 1 mole calcium and 2 moles of chloride per liter. All right? We have to use the stoichiometry of the compound to figure out what concentrations we have. Okay, let me show you. For an example, what's the molar concentration of the ions from sodium phosphate and 0.15 molar? So we're given the formula of the compound, or we can be given the name and the concentration, and we need to find the concentration of the individual ions. In order to do this, we should write the dissociation expression for the compound. In this case, sodium phosphate will dissociate into 3 sodium ion and 1 phosphate ion. So and then I'm going to use this to do the stoichiometric dissociation to determine the concentration. So 0.15 molar sodium phosphate. For every 1 mole of sodium phosphate, only 1 mole of sodium exists in solution, right? So if the concentration of 0.15 molar, then the concentration of the phosphate ion will be 0.15 molar. For the sodium, on the other hand, is different. We start with 0.15 molar sodium phosphate. Then for every 1 mole of sodium phosphate, 3 moles of sodium are produced. That means my concentration is going to be 3 times as high. All right? All right, try the following. Go ahead and pause the video and try to solve these. Then come back and check your answer. 0.25 molar magnesium bromide. I'm going to have 0.25 molar magnesium and twice as much bromide. That'll be 0.5 molar bromide. For here, it's going to be twice as much for sodium, same as for carbonate. And this one is going to be twice as much for the ferrous ion and 3 times as much for the sulfate ion. So we end up with the following. 0.25 magnesium ion, 0.5 for the bromide, right? If we start with 0.25. If we start with 0.33 molar for sodium carbonate, then twice as much for sodium ion because of that 2 right here. So it'll be 0.66, and carbonate will stay the same. All right, for the ferrous sulfate, twice as much for the ferrous ion, so we'll multiply this by 2. We end up with 0.15 molar, and 3 times as much for the sulfate. That'll be 0.225 molar. So we talked about percent and molarity, and those are the 2 most common things that I'm going to be testing you on in Chem 10. Now there's one more thing I'm going to talk about here, and that would be solution dilution. If I were to take a solution that is concentrated and put a small amount of it in another beaker, then add water, I should be able to calculate what the next concentration is using the following equation. M1V1 equals M2V2. Keep in mind, let me emphasize this. You can only use M1V1 equals M2V2 for dilution problems, not stoichiometry. I can't emphasize that enough. You cannot do it for stoichiometry. M1 V1 applies only to solution dilution, not stoichiometry. If you're working in the lab, you should always add acid to water, not the other way around. But since we're not going to be diluting anything in Chem 10, you don't have to worry about it. But if you take some more classes later on, that's something you need to know. Let's see how dilution works. If I were to take a solution that has 12 molar stock solution, and I like to make a solution with 1.5 molar from the 12 molar, and the final volume I want is 5 liter. How much volume do I need to get out of this 12 molar in order to make my solution? The way you do it is as follows. M1 V1 equals M2 V2. So I'm looking for V1 in this case from the stock solution. So I'm going to rearrange this equation to be M2 V2 over M1. That would be 1.5 molar times 5 liter over 12 molar will give me 0.625 liter. The way you would prepare this, you would take 0.625 liters, pour them into this empty flask, then add enough water to reach 5 liters, and you got yourself the diluted solution. Now that dilution works either you have molarity or percent or parts per million or whatever it is. All of it works. Alright, so try the following. Determine the concentration of the following solution. Go ahead and pause the video, come back and check your answer. So I want to make a solution by diluting 125 milliliter 0.8 molar hydrochloric acid to 500. So V1, M1, and that's V2. I'm looking for M2 in this case. So I'm going to use this equation, and M2 will be 0.2 molar. Same thing right here. I'm going to add 200 milliliter of water to 800 milliliter of 400 ppm. So M1 is 800, V1 is 800, M1 is 400. What am I doing? V1 is 800, M1 is 400. V2 in this case, you're adding 200 to 800, that's 1,000. Okay, so that's V2. V2 is 1,000. So we're looking for M2. We plug in the values, rearrange the equation, and solve for M2, and it's 320 ppm. Last part of this chapter is going to be stoichiometry. This stoichiometric part right here, I'm not going to discuss. We already talked about it. It's this part right here. If you're given a volume and concentration, you should use molarity to figure out mole. That's the only difference here. So let me show you with an example. How much 0.125 molar sodium hydroxide solution do we need to completely neutralize 0.225 liter of 0.175 molar sulfuric acid? So I am given the concentration of sulfuric acid as well as its volume and the concentration of sodium hydroxide. I want to figure out what volume I need of sodium hydroxide. So since I don't know what sodium hydroxide is, the known is sulfuric acid. That's what I will start with. I start with its volume, then multiply it by the molarity. I get the moles of sulfuric acid. Then from the equation, I need to write a balanced equation right here. It says for sulfuric acid, I need 2 sodium hydroxide. So I'm going to use that ratio right here, 1 mole of sulfuric acid to 2 moles of sodium hydroxide. This will allow me to convert it to sodium hydroxide. Then I can use the molarity of sodium hydroxide as a conversion factor to find the volume. So we start with the volume of sulfuric acid times molarity. This will allow me to convert to mole of sulfuric acid. Then mole to mole ratio from the equation, I will convert from moles of sulfuric acid to moles of sodium hydroxide. Then I'm going to use the molarity of sodium hydroxide to get the volume of sodium hydroxide. All right? Try this one. Go ahead and pause the video, try it, then come back and check your answer. What volume in liters of 0.0623 molar barium hydroxide are needed to react with 0.438 liter of 0.107 molar hydrochloric acid? Step 1, we write the equation, the balanced equation for the neutralization reaction. We're given the volume of hydrochloric acid as well as the molarity, the volume and the molarity of both hydrochloric acid and barium hydroxide. So I'm going to go from volume of the known hydrochloric acid using its molarity will allow me to convert to moles of hydrochloric acid. Then I'm going to use the mole to mole ratio from the equation right here to convert from moles of hydrochloric acid to moles of barium hydroxide. Then I'm going to use the molarity of barium hydroxide to convert to volume of barium hydroxide. And that's basically what stoichiometry is about. That's why I said I'm not going to spend too much time on it, because you already know how to do stoichiometry. It's just the only difference is this part right here, where we use volume to convert to moles, or we use molarity to convert from moles to volume. Okay, volume to moles using molarity, or mole to volume using molarity as well. The last part of this chapter I am going to skip. So we are not going to talk about colligative properties. All of this stuff, you can read it if you want, but we are not going to talk about it. What I will talk about is osmosis. Osmosis is a process that if you have two solutions that are separated by a semi-permeable membrane, then water will move from the side of high concentration of solute to low concentration of solute. This is known as osmosis. And if you were to apply a pressure that can prevent water movement from low concentration to high concentration, this is known as the osmotic pressure. Okay, the osmotic pressure is the amount you need to apply to prevent water from moving. This is important because of red blood cells. If we were to take a normal red blood cell and place it in a solution that contains the same amount of salt inside and outside of the red blood cell, it will exist as normal. We call that solution isotonic solution. If I were to take that red blood cell and put it in a solution that contains higher concentration than water, then water will rush, and if it's higher concentration, we call it hypertonic solution. Water will rush from the cell to outside, and it causes crenation of red blood cell. If we were to place it in a hypotonic solution, in other words, the concentration of salt is greater inside the red blood cell, then water will rush inside the red blood cell and cause it to swell and burst. This process is known as hemolysis. And that's the end of this chapter.